Morning. So today there is no fan. I'm in a better position, except that mosquitoes are. So for a change, it's good. So last week after the class is over, so Narayana came up with very good analysis of this loop, the next loop. So it made me, kind of think that I should revisit this and revisit these ideas one more time and make it a little bit more concrete for you. So here, when we want to, so the first thing is, when we think of dependency analysis, there are two kinds of dependencies. So here, one is intra-loop dependency and other is interloop. And of course, when we say dependency, there are there's a flow dependency, anti-dependency. So broadly speaking, we have these three dependencies: flow, anti, and out. Among these dependencies, these three dependencies, flow dependency is it's hard to resolve it because that is a function of the program logic itself. Whereas other dependencies, to some extent, we can find ways to get around the problem. So here there is one intra-loop flow dependency that is from statement 1 to statement 2. There's a value that is being produced here and that is consumed here. This is intra-loop flow dependency. This is also called as loop-independent flow dependency. This is loop-independent or intra-loop. So these intra-loop flow dependencies or any kind of intra-loop dependencies, they affect ILP, instruction level parallelism, because the instructions within a loop, the processor tries to execute in parallel. The scalar processor, there is only one thread, single thread within the processor. It tries to execute the instructions in a loop in parallel, and all these loop independent dependencies, they affect the instruction level parallelism. And then, so the interloop dependencies, they also affect vectorization opportunities also. They will affect, but in any case, so, but definitely, ILP gets affected. So now what we want to understand is this loop carried flow dependence. Okay, loop carried dependence in general. So let's say if you see this one, if you take a line, let's take it here. Let's put it here. So here there is iteration. This is 1, iteration 2, and iteration 3, and iteration 4. Of course, in this particular case, there are only 4. There is only 3 iterations, but but usually it will be more, right? So these are the iterations. So this is a single nested loop. So you can plot the iterations in 1 dimension. And if you take 2 iterations, so we say 2 iterations, there is a loop carried dependency between 2 iterations. If the read set of I1, let's consider iteration I1 and read, and the write set of I2, if it's not equal to null. Okay. That means they are read and writes are happening to the same memory location, or the other way around also, write set of I1 or intersects with read set of I2. Actually, this is even if write set of, even if write sets also intersect, we are in trouble because it causes output dependence. Now, in this particular case, if the way the array A, it cannot induce any of the dependencies because there are only reads there. But if you look at array X, okay, then there could be interloop dependencies. So like, for example, here, there is a, so let's consider just one, if take two iterations. So this write and this read, it is not possible for this write and this read to induce loop carry dependency because they have the same index. So, but if you consider this this one, this and this, there is a possibility. So now let's consider in when do we get this dependency? So if you look at the right set of I1, in the right set of I1, it consists of x of I1. And if you look at another iteration read set of I2, the read set of I2 consists of x of I2 comma x of I2 minus 1. So if for x of I1 and x of I2 to be the same, I1 should be equal to I2. If I1 is equal to I2, then it's a loop independent dependency. It's not a loop carry dependency. So these two pairs we don't need to consider, but these two pairs we should consider. So that means for these two pairs, for these two array accesses, to access the same memory location, we need to have I1 is equal to I2 minus 1. That means I2 is equal to I1 plus 1. So if I1 is equal to 1, then I2 is equal to 2. Then that means there is a dependency from when I1 is equal to 1. When I1 is equal to 1, then I2 becomes equal to 2. Then that means there is a dependency from iteration 1 to iteration 2. Similarly, when I1 is equal to 2, then I2 becomes equal to 2. Then I2 becomes equal to 3. So there's a dependence from iteration 2 to iteration 3. And you can continue this. Okay, if as the value of I goes, so this is what is called as a dependency. So this particular approach that we have taken in order to compute the dependencies, in order to figure out the dependency structure of a loop, we can generalize it. We can generalize it. So here, in order to make it kind of little bit more kind of concrete, so this condition I1 is equal to I2 minus 1. So of course, these two are equivalent conditions. Just because these two conditions are equal doesn't mean, in this particular case, this is a trivial example, so it will induce dependency. But otherwise, this has to be equal to true, or if you write it in a different way, you can say I1 minus I2 is equal to minus 1. So if you are able to find a solution to this, what is called as a linear Diophantine equation, I1 minus I2 is equal to minus 1. And we not only have to find a solution, we have to find a solution in such a way so that I1 and I2 lie between 3, because you may be able to find I1 and I2 which satisfy this thing, but the solutions I1 and I2, these values, if they don't fall in this range, then again there is no dependency. Are you with me here? This is the final formulation that we got. This is the final formulation. If you are able to say that no, there exists I1 and I2 which satisfy these two constraints, then that means there is a dependency in this. All right. So now let's go ahead and try to solve this, analyze the next loop that we have. So this is the loop that we have. So now, I'll write it here. Okay. So here, let's say, look at the read set of the read or yeah, okay. Let's see how it goes. So the read set of x of iteration I1 comma J1. Apologies for my handwriting. So this is x of I1 comma J1 minus 1 and x of I1 minus 1 comma J1 minus 1. This is the read set of the iteration I1 comma J1. Similarly, now if you take the write set of another iteration I2 comma J2, then the write set is x of I2 comma J2. So now in order to see whether there is a dependence between iteration, we want to check whether there is a dependence between these two iterations, I1 J1 and I2 J2. So in order to do this, like for example, then what happens is, what we get is I1 is equal to, so now let's analyze this and this. Okay, this particular read and this particular write. So in order for these two to point to the same memory location, so I1 should be equal to I2 and J1 so what do I say? J1 minus so J1 minus 1 is equal to J2. So in other words, this gives us I1 is equal to I2 and J1 is equal to J2 plus 1. All right. So now if you look at the iteration structure here, this is 0, this is 1, this is 2, this is 3, this is 4. This is a two-dimensional iteration space, 1, 2, 3, 4, so on and so forth. So what we are getting is for the same outer iteration space, if let's say if I1 is equal to 1 and I1 J1 is equal to this is I1 J1 is equal to 1 comma 1, then or let's say I2 J2 is equal to 1 comma 1. Let's make it like this. Okay, let's say I2 J2 is 1 comma 1. Then what will be I1 J1? It will be 1 comma 2. Okay, are you with me here? So that means, so if you look at I1 J1 is a it's a read. Is it a write? Yeah, we are writing. This is good. So this is 1 comma 1. So there is a dependence from here to here. Are you with me here? 1 comma 1. There is a dependency from 1 comma 1 to 1 comma 2. In iteration 1 comma 1, what are we doing? In iteration 1 comma 1, are we doing a write or a read? Are you with me or you're lost or what's the deal? In iteration I2 J2, let's take the iteration I2 J2. I2 J2, we took it as 1 comma 1. There is a write happening, right? Okay. What is the dependent iteration on this? The read is happening in the iteration 1 comma 2. Yes or no? Because J1 is equal to J2 plus 1 and I1 is equal to I2. So what is happening here is there is a dependence from 1 comma 1 to 1 comma 2. Similarly, there is the whatever the write that is being generated in the iteration 1, 2, it is being consumed in the iteration 1, 3. So these vertical arrows that you are seeing in this picture that says you fix the outer loop I, and there is a loop carried dependency in the inner loop. Are you all with me here? You fix I and you are iterating through the inner loop. And for a fixed value of I, the value, the simplest way to look at it is, so j and j minus 1, if you see, the value that is produced in the previous inner loop iteration is being consumed in the current inner loop iteration. Okay, that is the summary statement for this. So what we are getting is, so we are able to establish these vertical dependencies, that is the loop carried dependencies within the inner loop. So this is the loop carried dependency within the inner loop. So like that, for every value of I, you get a loop carried dependency within the inner loop. Now, if you do a similar analysis, okay, if you do a similar analysis, let's do so the similar analysis, we want to now compare this read with this read. This is the second analysis that we would like to do. And both this write and this read, they will, what do you say? They will access the same memory location if I1 minus 1 is equal to I2 and J1 minus 1 is equal to J2. Are you with me here? So what we have is I1 is equal to I2 plus 1. I1 is equal to I2 plus 1 and J1 is equal to J2 plus 1. So that means if I2 J2, in the iteration I2 J2, if I make a write, it gets consumed in the iteration I2 plus 1 and J2 plus 1. That is in iteration 1 comma 1, let's erase this one. If in iteration 1 comma 1, so here, if in this iteration, whatever the value that is being written, it is consumed in iteration 2 comma 2, because I1 is equal to I2 plus 1 and J1 is equal to J2 plus 1, and this is the iteration in which this read is happening. Similarly, whatever you produce in this iteration, in iteration 2 comma 2, it is getting consumed in this in the iteration 3 comma 3. So this picture that you are seeing is what is called as a dependency diagram. Okay, this is what is called as a dependency diagram. We are looking at it visually, but if you think from the compiler perspective, it tries to encode this as a collection of integer linear equations. Okay, are you all with me here? What is the in order to complete this, the way we say is, these, in order for to have a dependency between this read and this write, we need to see whether there exists I1, I2, J1, J2 which satisfy this, and along with that, the constraints are, less than 3. So J1, J2 less than 3, because the dependencies, the solution should lie within this space. Okay. And since you're all, if you kind of look into, if you recall maybe your linear programming from your +1 and +2, if you have a collection of linear inequalities, these are linear inequalities, right? So if you have a collection of linear inequalities, so like for example, one linear inequality, like it says all the points which fall in this side, they, they satisfy that linear inequality. And then you can have another line, maybe I'll just, so you can have another line which is going like this, and which says everything going like this, it satisfies. So what happens is, and then we can have another thing, which this could be another linear inequality. All these linear inequalities, what do they enclose? They enclose a polyhedra in 3-dimensional space or a polygon in 2-dimensional space. So what happens is, these iterations that we have here, these constraints, these iterations, they generate constraints. All these constraints, they define what is called as an iteration space polygon in a 2-dimensional space. or an iteration space polyhedra in a multidimensional structure. Okay. So now what we want to do is within this multidimensional structure, now is the constraints that we have, is the inequalities that we have mentioned here, whether they satisfy, whether there exist solutions in this integer polyhedra or integer polygon. Now for these equations that we have set up here is what the compiler looks for when it does this loop dependency analysis. And this whole area of compilers is called as polyhedral compilation. It's a very, very interesting area of work, polyhedral compilation, where what we do is we take loops, we look at the iteration space defined by the loops, and then we try to check, look at all the integer points which fall in this polyhedra or polygon, and then see whether those integers induce any kinds of dependency on the statements which are present in the loop. We don't need to understand all those things right now, but what I would like you to be able to do is, given a loop like this, will you be able to draw this picture is what is essential. Because once you draw this picture by looking at the loop, we understand the dependency structure in the loop. So why is this dependency structure important? Why is this picture, why is this important? What does this, when you look at this one, what does this tell you? Is it possible to execute the inner iterations of the loop in a parallel fashion? Can I execute iteration j for a fixed value of I? You fix I is equal to 1, and there are 3 values for j. J is equal to 1, j is equal to 2, and j is equal to 3. And let's say the whole loop body, no, you just call it as h of ij. Then this is then the loop body is can I execute h of 1 comma 1, h of 1 comma 2, and h of 1 comma 3 in parallel? Yes, we'll come there. So right now, for a fixed value of I, you fix a particular column. You cannot execute this in parallel because there's a dependency between them. There's a loop carried dependency between them. Are you all with me here? So this is the dependency structure that comes out. But for a fixed value of j, can we execute all these loops in independent of each other? All these things. For j is equal to whatever, for j is equal to 1, for different values of I, we will be able to execute this. Right? And then after the j is equal to 2, and then we can execute this. And then after j is equal to 3, we can execute this. After j is equal to 4, we can execute this. Are you all with me here? And how can we accomplish this? How can we make this possible? Can we rewrite this loop as for j is equal to 1, 2, 3? For I is equal to 1, 2, 3, you do a loop interchange, and then you have the loop body, and all you have to do is no, you put a you parallelize this inner loop now. Does this work? You are taking a fixed value of j, you are iterating through every row, and then another row, another row, another row, but the computations within the row, you can execute them in parallel. Either you want to vectorize them, you want to use multiple cores, it depends on. Is there any other way of, is there any other parallelization strategy? Right now, if you think about it, you can execute at any point in time 4 iterations in parallel. This particular, can we do better than this? Think about it. Okay. So now let's say I have a question for you. because let's say now we change the loop. So the first question for you is, what kind of accesses should be there in the loop so that we end up having dependencies like this? We not only have these dependencies, but we would also like to have dependencies like this. What kind of accesses we should add here in the loop so that we end up having this kind of dependency? Is there anything we can add here? This is x of I minus 1 comma j. It will do the trick. Does this work? Yeah, I think it should work. So now, can we parallelize this loop? Can we execute rows in parallel? Each row in parallel we cannot, no? Each column also you cannot parallel. So is this hopeless? So we can use diagonals. Excellent. So what we can do is we have to write the loop so that no diagonals can be executed in parallel. Can you rewrite the loop so that, how can you rewrite this loop so that you execute the diagonals? Think about it. Lots of interesting challenges coming when you try to parallelize this loop by going across the diagonal. Okay, but you get the picture, right? So when we are trying to, one of the biggest sources for parallelization is loops. Of course, there is task parallelism, etc. We will look at that at a different time. But loops are one of the biggest sources of parallelism. And when we want to parallelize loops, there are three things you have to keep in mind all the time: vectorization possibility, multi-threading possibility, and locality. So locality we will not see in today's class. We will look at multi-threaded parallelism now. So these are the three things that we have to do. And in order to see whether the given loop is parallelizable or not, we have to understand its dependency structure. Compilers will try to do their bit, but usually, we never have code as simple as this to get a very clean analysis. Okay, because we end up using pointers, we end up using so many things, and when the compiler does, conservative analysis, most of the time it gives up, except for few standard programs. But as a programmer, if you are aware of what is happening in your program, then you might be able to rewrite it. Like for example, here, if the compiler didn't do a loop interchange to parallelize, then you should do it. You look at the optimization report, and the optimization report says, hey, says it's not in this case, in the previous case. You look at, you compile the code and look at the optimization report and see if the compiler did a loop interchange and try to parallelize. And if the compiler didn't do it, you have to do it manually. Okay, maybe the compiler didn't do it for whatever may be the reason, we don't know. Okay, but as a programmer, you can do it. All right. So one more before we move on. So here, in the last case, we said, we can vectorize the last loop, provided the width of the vectorization is not greater than 15. Okay. So how do we specify that? Like if you go to when we want to do vectorization, what we usually put is, this is what we do now, hash pragma OMP SIMD. If you kind of add this option, safe len 16, then that means what the compiler will, you are telling the compiler, like up to 16, it's okay. Beyond 16, dependencies are there, so watch out for it. Okay, safe length is what is the safe length for the vectorization width. So you should try to explore these pragmas in detail and see how they can be of help for you. In the class, we cannot go through these things extensively, but you should look for the different options that you have for the pragmas and see how you can use them. All right. So now let's move on to multi-threaded parallel. Now we looked at vectorization and the dependency analysis that we have talked now. It is equally applicable when we are trying to exploit multi-core parallelism. Okay, let's start with it. Great. So again, to bring you back, the original, kind of taking a step back, and this is the architecture of, again, this is the architecture of typical processors on your system. Your system may be a quad-core processor with high likelihood. If not a quad-core, definitely a dual-core, and every core has a SIMD unit. And there is an L1 I cache, L1 D cache, and then there's an L2 cache, and there's an LLC. Well, the cache hierarchy kind of differs from one architecture to another architecture, and especially from one manufacturer to another manufacturer. Like, for example, if you take an AMD processor, the cache hierarchy in AMD could be very different from the cache hierarchy in Intel. So just watch out for it. This is one representative picture. And what are the dimensions of optimization? You can see. So vectorization, thread level parallelism, memory locality, cache interference, and of course we can always work at the algorithms level. In the Monday class, Monday 2 o'clock class, we are supposed to have a makeup class. In that class, we will look at memory optimizations in particular. Okay. So that's the plan for today, for the rest of the today's lecture and for Monday. So now the first question for you is, what is the difference between processes and threads? You did OS course, right? What is the fundamental difference between processes and threads? Multiple processes can also execute simultaneously.
They have the separate registers, processes. While threads don't share a lot in common.
What all the things threads share?
Heap memory.
Threads share heap memory. Okay. What else? You can bind processes also to core, I guess. A process can't execute multiple instances of itself without. What is, from programming perspective, what is the biggest challenge that you see when you are programming, when you are trying to do parallel programming using processes versus threads? From a programming perspective, let's say you have a parallel quicksort program you want to write, or no. So what is the parallel quicksort strategy? It's very simple. Find the partition and both partitions are sorted in parallel. Yeah, exactly. So that is the biggest problem. Every process has its own data segment, and the address space of every process is completely isolated from the address space of other processes. And the only way the processes can communicate with each other is through explicit inter-process communication mechanisms, such as pipes, or you have to define an explicit shared memory, or messages. We can send messages between processes, etc. So the inter-process communication mechanism is quite heavy, because every process is completely isolated from the other process. Okay, the address space of every process is isolated from the other process. But when it comes to threads, they share the same code segment, they share the same data segment. Lots of global structures threads share among between them. Every thread has its own stack, otherwise it cannot execute, and every thread will have its own register set, because again, in the that will, if registers and stacks are not separate, then the two threads will interfere with each other. So stack is essential for the thread to do its own computation, and so are the registers. But a lot of other things are shared. Because of that, it is very easy for threads to communicate with each other. So, and also depending upon the implementation, threads are lightweight when compared to with processes. Okay. I think in your operating systems course, you would have written a bash, a shell program, right? So what IPC mechanism you use it in order to implement more, or in order to redirect output of one to another? You use it pipes, right? So pipe is one standard intercommunication mechanism, inter-process communication mechanism. But threads can communicate with each other through shared memory. That means one thread writes to a particular location. So like, for example, if you see in this picture, this thread writes to this, and this thread can read it from here. Okay, so that is the inter-process communication mechanism. In the case of threads, can happen through shared memory, and that is the biggest advantage of threads. It's easy to program. You can, but I think it's more, it may not be efficient, and it's not. It's more harder to do it. Great. So now, what is our goal? Our goal is to write programs so that we can use all the cores that are available on a system. Okay. Of course, we can use pthreads to do it, and on a processor, if you have a server with multiple cores, you can have different applications, and you can say, no, this email, the web server should be is pinned to core 0, and database server is pinned to core 1, and some other server is pinned to cores 3 and 4. Like that, the available cores on a system, it can be allocated to different processes that are running on the system, and these processes can correspond to the same application, or they can correspond to different applications. They can correspond to different applications. These days, I don't know whether you studied or not in any of the courses set. So there is a lot of interest on what is called as service-oriented architecture or microservices-based architecture. Right now, when you write your application, your whole application is just one monolithic program, right? You compile it, you run it, and one program runs. But now, in a microservices-based architecture, your whole application is thought of as a collection of microservices. And these microservices communicate with each other through well-defined API. So usually there is something called as a REST API, which is very popular. So anyway, the point of this story is, if your application is a collection of microservices, different microservices could be running on different cores of your system. Okay, that is how you can achieve application level parallels. And also, when you work at the microservices, that level where the microservices talk through well-defined web API, one microservice could be either present on the same computer, or it could be present on a different computer. It doesn't matter, because the inter-microservice communication is via the web API, not through shared memory or any of these mechanisms. So this is, so keep that in mind. This is one way of utilizing the available compute power on your system. But of course, next comes the high performance computing applications where they are quite different from these kinds of applications where you have a web server, database server, user authentication server. These are the kind of applications you may see in practice, but in HPC you have this supposedly there is an algorithm, and the algorithm, if you run it using single core, it will take 1 week, and you want to get the job done in 1 hour. Okay, so from how can you bring it from 1 week to 1 hour? So then you have to parallelize your program. You have to understand the parallelism structure in your program, and you have to parallelize it. So again, for the time being, we will focus on no parallelism that is available from the loops, and usually, so that is the focus of our lecture. And but it's important because many scientific applications, we have these linear algebra problems which are coming from linear algebra space, where we have to do vector arithmetic or matrix vector arithmetic or matrix arithmetic, so on and so forth. So you already know how to use pthreads and write multi-threaded programming. What did you do in your OS course for multi-threaded programming? What problem you did? Any project problem? What is the intro? Can you tell me one interesting problem you solve using pthreads? Hmm. Sorry? Multi-threaded server. Okay, okay, I see. Okay, okay, got it. Yeah, nice, nice. Very good, very good. Well, so, but when we use pthreads, you have to use pthread create, join. There are a bunch of library functions, the semantics you need to understand it properly, and all those challenges are there. So OpenMP approach, OpenMP stands for Open Multiprocessing Standard. Using this approach, it is possible for us to write multi-threaded programs very easily. Like for example, here, this is your C code, and there is a chunk of code which is in left and right, this scoped code, left and right flower brackets. So what happens is when there is a single thread that comes, so there is a single thread of execution that keeps coming, and when it hits this parallel region, which is annotated like this, then what happens is multiple threads will be created. Okay. So the number of threads you would like to have, you can specify it as a part of the program, or like for example, at the command prompt, you can say export OMP num threads, something like that is equal to 6 or something like whatever the number of threads that you would like to have, you can specify. And if you don't specify anything, the default number of threads that gets generated is equal to the number of cores that are available on your system. So one nice thing that I would like you to notice here is, if you write OpenMP code and you run it on a dual core system, or you run it on a 6-core system, you don't need to go and change the source code in order to change the number of threads. The default, of course, it looks at the default number of cores and picks up that generates that many number of threads. The other way is through environment variables. Through environment variables, you can control the OpenMP runtime system. The OpenMP, you tell the OpenMP runtime system, I would like to have 6 threads, or like for example, you may have a 6-core system, but the other 4 cores are already busy doing something. So you want to use only 2 cores. So you want to use only 2 threads or 3 threads. You cannot go and change the source code because first of all, you may not have source code with you. okay, because someone shipped that that software to you, so you cannot go and change the source code. So you can control the runtime system by using this. So by using these environment variables. Okay. So now let's try to run this program. So you can see this is the OpenMP function, OMP get max number of threads. It tells us the number of threads that are available, and when we go here, so it executes all the threads execute the same statement, and the thread if every thread prints a message with its thread ID. Let's go here. Action closed. Great. CD OpenMP code. You can see it's the same OpenMP code here. And so let's compile this code. GCC -f OpenMP hello openmp.c. See every thread. So the output, there are 12 threads because I have 6 cores, and every core has 2 hyperthreads. So it picked up 12 threads. And so what is the biggest challenge in multi-threaded programming? Yeah, when you run, it's not the same thing that is running it. So many things determine, which thread comes executes first. Like I have 12 threads. What are all the different possible number of different outputs that can be printed on the screen? How many? 12 factorial ways. So there could be a bug in one out of these 12 factorial ways. Okay, and this will be so this could be produced on the client system, and he says, hey, my machine crashed and please solve this problem for me. And you take it back and you will not be able to reproduce it, because you keep on running, you don't have any control on what is the schedule. So that one particular trouble, execution sequence which is causing the trouble, it's not even picking up in your system, so you cannot even reproduce the code. So when we do multi-threaded programming, of course, this is reproducibility is a very, very important thing. So if there is a way for us to say, if there is some problem, some issue, if there is a way for us to trace back and say, this particular interleaving of instructions gave me this problem, then people will just allow you, because it's problem reproduction is just nightmare. Okay. Or in our context, you, while giving the demo to the TA, it crashes. And so there are 2 ways of looking at it. You can say I debugged everything and it never, it's not a problem, but on OJ it crashed. Okay, it's bad luck. But you can challenge the TA saying, no, you reproduce the problem again and show it to me. Then I will accept, that there's a problem in the program. Okay, anyways, so jokes apart, so this is a very important thing that as you keep executing, there are different possible ways of interleaving this code, and that's a primary problem in multi-threaded code. Oh, well, let's we can change the number of threads. Let's see, export OMP underscore num threads is equal to 4. Let's see if it has, great. So now we have only 4 threads. Okay. Let's get back again here. Where are we? So this is the OpenMP. So the execution model is what is called as a fork join execution model. So whenever there's a single master thread and when it hits a parallel region, multiple worker threads are generated, and the multiple worker threads they execute the parallel region. And once they are out of the parallel region, we have what is called as a barrier here, and all the threads will be blocked. So there is a barrier. All threads will be stopped here. And then after all the threads are synchronized, again, we move forward. So this is the execution model of OpenMP. The next important idea is the memory model. Okay. So what happens is, everything that is there, whatever. So let's go back here. All the data that you have, let's say, if you have a variable int a that you have declared, this variable a, it is shared across all these threads. Okay, it is shared across all these threads. Well, it's good because now the threads can communicate with each other through the shared variable. Otherwise, the threads may have to talk with each other through messages or something like that. But through this shared variable, they can talk with each other. But let's say, like this comes out of, if you go and look at the original source code, this may be coming from something like hash pragma, OMP, parallel, and then here and here. And then here, if you have int b, this b is a private version for this b naught. There are different versions of this b, b3, b4 that will be generated. So the variables that are declared within the scope, they are private to every thread. It is important to have private data because otherwise the threads cannot do compute anything, because if everything is shared, then it's going to be a pain. Okay. So this is the memory model, parallelism model. So as you can see here, the variables a and b, in the absence of this, ignore private and share it for the time being. In the absence of this, both the variables a and b are available here, but you can tell the OpenMP system or the compiler that keep the variable a private by using this. That means every thread will get its own version of variable a, and every thread will get but the variable b is shared among all the threads. Are you with me here? The second, of course, is this one. So the variable b is shared among all the threads, and the variable a is private to every thread. So this is a memory model. In general, if you see you have a collection of threads, and every thread has its own small private memory, and they all communicate with each other through a shared memory. This is the model, OpenMP memory model. Any questions here? You're all doing all right? So now when we come to loops, like you have different iterations of the loop, and these different iterations of the loop, they can be executed subject to these dependency constraints. They can be distributed to different cores that are available in the system. Let's see how this works out. Okay, like for example, now here, pragma, OMP, parallel for, and so what this says is, the for loop that is there below, execute it in parallel. Okay, different threads will execute different iterations of the loop in parallel. Let's see if it makes any sense for us here. I didn't write code for it here. Let's check if we can quickly to hello for.c. What is the syntax? We just have to use parallel for, and for I is equal to 0, I less than 10, this plus I. Yeah. Variable is shared. No. No. Things can go wrong. So what we do is, no, we will do one thing. So we will say TID is equal to this, and loop ID, LID, loop iteration ID, iter ID is equal to %d. See what happens. ICC, let's use for ICC, this is how you should use. So -q OpenMP and hello for .c, vi hello for .c. I don't know what happens to that I itself. No? Is it I will be private or? For loop into? Okay. Yeah. So, okay. Let's see. You can see, here loop 0 is assigned to thread 0. And what is iteration 1 is also assigned to thread 0. Iteration 2 is also assigned to thread 0. Iteration 3 is assigned to thread 1. Iteration 4 is assigned to thread 1. So if you think about it, this is what is happening. Iterations, iterations 0. Can you tell me 0, 1, 2? 0, 1, 2, they are allocated to which thread? Thread 0. Iterations 3, 4, and 5, they are assigned to one thread. And 6, 7, 8, 9, no, 6, 7, only 6, 7, no? Thread 2, iteration 6 and 7, thread 3 is iterations 8. Okay. So different iterations of the loop body, they are assigned to different threads for execution. That's what, and this is what is called as a iteration scheduling or loop scheduling. And there are different loop scheduling or iteration scheduling strategies or loop scheduling strategies that we will see now. Are you all with me here? Any questions you would like to ask, or you're all doing good? Sorry? Yeah, please go. Okay. That is true. That's the problem is they have to do very conservative estimates. They have to, when they do analysis, compilers, their primary goal is to preserve the semantics of the program. Semantics under all conditions, semantics which are there in your mind, but no assumptions which are in your mind, but not there on the. Yeah, it will do it. That is the auto parallelization. It's a lot of people, lots of all compilers they attempt, even GCC, ICC, they do try. Sorry. No, I think if you like, for example, you look in ICC kind of options which will try to auto parallelize. But I think if I'm right, people stop putting effort on it because there's a lot of effort, but returns are small. GCC has this thing called as graphite, which does auto parallelization, GCC graphite, and LLVM has, or Clang has poly, which is no, which also tries to do some kind of auto parallelization, etc. It's a valid question, and in fact, the whole area of research of polyhedral compilation is for that one. How do you do analysis? How do you parallelize? And okay, so an alternate way of parallelizing for loop is you create a parallel for loop here. Okay, so not so you create a parallel region here. So multiple threads will start executing. And this private underscore number, no, whatever, some private variable, every thread will have its own private variable. And then once they hit that for loop, the iterations of the for loop will be shared between these multiple threads. Okay, like for example, maybe, from 0 to 100, this thread, and 101 to maybe 200, this thread, so on and so forth. When they hit the for loop, they will do this thing. So now we will talk about loop scheduling. So when we hit a parallel for loop, the iterations of the loop, how they are distributed between different threads. The first approach we have already seen, which is the static scheduling, where a collection of threads are allocated to this. Is in this particular case, there are 4 threads. Some collection of threads are allocated to thread T0, and the next collection of threads are allocated to T1, the next collection to T2, the next collection to T3. This is static schedule. So they are equally divided. But if you specify this parameter called as 4, then what happens is the way things get scheduled is the first iterations go to T0, T1, T2, T3, and then again it will go to T4, not T4, sorry. Again it comes back to T0, T1, T2, T3, so on and so forth. Do you understand static scheduling? And why do we think, is there any reason? Do you think this 4, etc., will have any impact on the performance of the program? Let's say there are 2 approaches I have. Static, I'm taking one extreme approach, static one versus static 16 or 32. Do you think this will have any kind of impact on the performance of the program? Whomever tells this, they'll get a good chocolate from me next course.
There will be some overhead.
Okay, overhead. Okay. Okay. Locality is better in, but even if you read, can you elaborate? Let's say what can go wrong in static one? Tell me what can go wrong in static. You're almost there, but still not there. Okay.
So that if it is only static, it is static one.
No, it's not static. If it is static, no, the whole thing will be, if you have 100 iterations, 4 cores or 4 threads, 25 iterations to each.
So it's static MP4.
Yeah, static n by 4.
First MP4 iteration for 2.
Yeah, that's true. First 10 by 4 will go to T naught, and then next 10 by 4 will go to. No ideas?
L2 cache is private to each and L3 is a common L3 cache. So if O1 modifies L2, it has to be reflected to L3 before go to DXA.
Okay, you're all getting there. Good start from Pramod and then you. So yes, you are. So let's say if you have 4 cores, C0, C1, C2, C3, T0, T1, T2, T3. What will happen is, everything will have its own private cache before LLC. Then let's say if you have a loop where you are just doing x of I is equal to x of I plus 1 for I is equal to 0, I less than whatever, some 1024 plus I, something like that. Then what will happen is with high probability, x0 to something like x4 will fall in the same cache line. Okay, so this is here, this is here. These are all caches. Let me draw a cache. These are all caches. So what will happen is this whole thing, it can fall in some particular cache lane here when T0 tries to modify x0 equal to x0 plus 1. So this chunk of data from the memory, it will be, let's say it is present here, it gets transferred here. In static 1, what happens is when T1 tries to modify x of 1 is equal to x of 1 plus 1, this cache line needs to be invalidated and it needs to be migrated to this cache line. And after this this executes, and then T2 says x2 is equal to x2 plus 1. So the cache, this cache line needs to be invalidated again, and this has to move from here to here, and then again it has to move from here to here. You can see the number of cache migrations. There are 4 cache migrations, and there's a very complicated protocol involved in invalidating other cache and moving the data from one cache to another cache, etc. But on the contrary, if it is static 16, then no, what happens is all this data, that all the data that falls within the same cache line, it could be here only, that is no locality which Pramod is talking about, in which case you can potentially avoid these cache migrations. Does it make sense? Because x0 to x4 update will be done by thread T0 only. So there is no necessity. So T1, T2, T3, they don't call or pull this cache line that is present in the cache of core 0 towards the cores in which they are present. Does it make sense? They're all good? Great. So now, if you think about it, this simple parameter can have a good impact on the performance of your program. 4 or 8 or whatever that is. So now let's move on. And then there is dynamic scheduling. In dynamic scheduling, what happens is the process, the runtime environment keeps on giving work to threads whichever are available. So here in dynamic, the default, when it gives the number of threads, by default it only gives, when it gives work, by default it gives only one iteration. But you can specify the parameter saying, hey, whenever you are handing over work, hand over work in in 4 iterations or 8 iterations, because what happens is coming back and taking work, it's a very expensive process, especially if the amount of work done in a loop is very small. You do some work, very small work, you come back and then again get one more small job and then again go back, do it, come back. So unless the amount of work that is being done in a loop is quite high, you don't want to use dynamic with one as the parameter. You may want to use dynamic with some parameter like 16 or 64 or 1000 or something. And then there is a guided thing here. In guided, what happens is initially you give out a big chunk, and as we progress, the scheduler gives us less amount of work, proportionately less amount of work to each of the threads. So you can see here, you start with a big chunk on the left side, and as you keep going to the right, the size of the chunk slowly goes down, and how slowly it goes down depends upon the number of iterations that are left for schedule. Okay. Usually what happens is, be it in dynamic, so when we do, why is static scheduling bad? Why do you want to even go for dynamic scheduling? No, but if you give first strategy here, static scheduling, no, there is no big deal. So sorry, if you have an infinite loop. Okay, I see. I didn't think about it. Good. Actually, I didn't think about it. So so dynamic really, I see the point here. When you make a disk IO, the thread goes to sleep. You have to wait for, in a particular iteration, you make a disk IO and you have to wait. When you go to sleep, then, but the other threads have finished the work, and they can get more work from the scheduler. So that is, but generally speaking, that is one case, very interesting case actually. What is the other, generally why you don't want to do static schedule? When the amount of work in the iterations are not uniform, then what if this thread T0 completes in 10 milliseconds, but the other thread takes 1 hour? It's not good, right? It may take 1 hour because of the reason, it could be doing some reading of, based on some condition, it could be reading some disk or something like that. So what kind of problems need static scheduling, and what kind of problems need dynamic scheduling, and what parameter sizes that we need to use? These are all some interesting problems to look at. And we can use auto, and we can also control the scheduling strategy, perhaps using runtime techniques also. So before I go further, so there is one interesting problem. So there is people know now machine learning all over the place. So in systems also, people want to use machine learning somehow. And one of the original problems, one of the original interesting problems is, given a loop, can you design a machine learning model which looks at the loop and says, for this loop, it does a classification which tells us static scheduling is better, or dynamic scheduling is better, or guided scheduling is better. It's a three-way classification problem. You know that you did some machine learning or not? There's one course now. So basic classification, did you study now or yet to study? Classification you have studied. So now you have a loop, and you want to classify whether the loop should be statically scheduled, dynamically scheduled, or guided scheduled. And of course, we also can kind of use, the problem is much more complex because it's just not mere static scheduling. We need to figure out the right parameter, 4 or 8 or 16 or 32, whatever is the parameter we need to determine. So in the machine learning problems in the classification problem that you have studied, what is the classification problem you looked at? In the one example you looked at in the course.
add weather conditions and classify whether we can play outside or not.
Yeah, yeah. Okay, standard stuff. Okay, so whether you want to play outside or not, or no more current is whether you should attend a class or not. So, well, there in that particular problem, you take some parameters, right, like temperature, some attributes, few things you take based on that. There's a feature vector representation of the day. Yes or no? The feature vector consists of the temperature, windy, and other light condition, and that's the feature vector. And based on the feature vector, you classify whether you should play outside or sleep or do whatever. But if you take a program, what is the feature vector representation of a program? Feature vector representation of a loop. We have this loop. Is there any way of representing what features you want to use while solving the classification problem in this context?
Cache size.
Sorry?
Cache size. But
Cache size is for a particular machine, the cache size is fixed. Okay, so you are building a model for a particular machine. Instruction? Instruction mix inside the loop. Okay. Okay, good. Instruction mix. Memory address is accessed. Okay, how do you get them, or how do you? Okay, good. Any more? Hmm? So it's actually a very good research problem. Okay, so it's a very representing. There's a lot of interest in applying machine learning strategies in the context of systems in the space of compilers. But the fundamental problem that we get in the space of programs or compilers, there are two problems. The first problem is what is an appropriate feature vector representation of a loop or a program? Because it's a structured thing, right? It's not like uh, so. So that is one problem. Second problem is, if you want to build what in order to build a machine learning model, what is required? Data. No? Yeah. So we need to have a training data, right? If you want to train a machine learning model for phase classification, all of us can take our camera out and take a photo of each other, and we have the training data available. But if you want to write a machine learning model to check whether whether we should what kind of scheduling strategy we should use for a loop, and the number of people who can write proper OpenMP programs are very few in the world. And it's not like you can take a photo and get it. Even if you scratch your head and try to write a program, it will at least take a day minimum. Okay, so availability of training data in the context of programming languages, it's used to be it's a very big challenge. So what do you do? Sorry? For data, yeah. How do you get training programs which you can use? So one way of doing it is, take UG1 programming course, and but that doesn't have OpenMP this problem, but you can use them for different purposes. 10 sorry. 10 years back, it was very hard, but now at least you can just go scrap GitHub and look for all the programs which contain some kind of OpenMP thing, and you might have some success if you scrap GitHub. Kishore seems to have some interesting ideas. You can share them aloud. About what? Uh-huh. Uh-huh. All right then. So now let's conclude the class. So we'll quickly talk about race conditions and so is this a cause for concern? This code?
Yes.
If this is not a cause for concern, you have a cause for concern. You should read operating systems course one more time. I don't want to again explain why this is a cause for concern, because you read that multiple threads try to read the same time and they add separately on their own, and when they write back, the write update doesn't happen. So that's a race condition. And how do you solve this race condition? You just put, if it is just one line, you can just use pragma OMP atomic. And if it is more than one line, so you can I say that it's a critical region. Okay, so. But then, of course, the problem is this kind of things are very quite common. So what happens is, if you do this, this is okay. But an alternate way of, in order for the compiler to optimize it, what it can do is it can tell this is that it is performing a reduction operation, and the variable total corresponds to that reduction, and plus is the reduction operation that is being used. So when you use that, compiler automatically generates code which doesn't cause any race conditions. Are you with me here? So because reductions are quite common, and you can use, there are different kinds of reductions that are possible. If you go look at what are the available reduction operations that are available, you can in the OpenMP manual or specification, you will be able to get it. If you don't have reduction operation, this is what you end up doing. So if you see, is total underscore thread, is it private to every thread? Yes, right? It is private to every thread. How about total? That is common to all the threads. So now what happens is, so this whole thing, the for loop, all the threads will execute independent of each other because this variable is independent. Okay, everyone has their own copy, and finally there is necessity for synchronization only on line number 10. Okay, so here this is the really bad thing, because every time a variable wants to update the total variable, it has to take the lock, increment, and then release the lock. So all the time, 99% of the time, threads will be fighting for the lock, and the time goes waste. So this is a bad thing, because the lock complexity or synchronization complexity is proportional to the number of iterations, so which is super bad. Okay, this code will perform terrible. But when you come here, the number of times you have to synchronize is equal to the number of threads that are present. So it's really good code. Okay. So, oh, sorry, it's 11:30. I'll stop here. And in